Hello and welcome back. In this video, we discuss about dimensional analysis, an important tool used in experimental fluid mechanics. In many problems, the analytical approach we have discussed earlier, such as integral and differential formulations, will be useful, but in other cases, we may have to do experiments for a feasible solution to a given problem. The dimensional analysis helps us to do meaningful experiments and collect and analyze data in an efficient manner. Dimensions of the basic physical quantities such as mass, length, and time are represented using letters M, L, and P respectively. For derived quantities, the dimensions can be derived from their unit. For example, unit of velocity is meter per second, therefore its dimension can be expressed as L by T or Lt raised to -1. Similarly, we can derive dimensions of physical quantities such as acceleration, force, pressure, coefficient of dynamic viscosity, etc. in terms of basic dimensions M, L, and P. Dimensional analysis can be used for deriving simple functional relationship between various parameters. For example, the pressure drop per unit length, denoted by delta PL, in a smooth pipeline can be related to various parameters such as mean flow velocity V, diameter of pipe D, density of fluid ρ, and dynamic viscosity of fluid mu. In order to understand how one parameter is influencing the pressure drop, we can do systematic experiments, keeping all parameters constant except one. For example, keeping V, ρ, and mu constant, we can measure pressure drop in pipes with different diameters. Intuitively, we can imagine that pressure drop will be less in pipes with larger diameters. In a similar fashion, we can keep d, mu, and ρ constant and change the mean flow velocity V, or keeping V, d, and mu constant and vary the parameter density. The experimental data shows that the pressure drop increases flow velocity and density. Although this is a systematic approach for doing experiments, it may not be practical sometimes. For example, an experiment changing kinematic viscosity, keeping density, velocity, and diameter constant is not practically possible. Moreover, a problem involving several parameters requires numerous experiments. In order to overcome such issues, the variables examined in the experiments can be combined to generate non-dimensional groups so that a functional relationship between these groups can be found out from the experiments. In the dimensional analysis, we use Buckingham's pi theorem for deriving such relevant non-dimensional groups. For example, we can identify two non-dimensional groups combining these four independent and one dependent variable delta PL. In this case, the first non-dimensional group that can be derived is d delta P by rho B square. In the dimension of this group, we can see that it is non-dimensional. Second non-dimensional group that can be derived is rho V d by mu. In this case also, we can see that it is non-dimensional. Now, we have 5 variables grouped into 2 non-dimensional groups, and we have only 2 variables to study. Therefore, the necessary experiments will vary the non-dimensional group without independent variable and determine the corresponding value of second non-dimensional group. The result of such an experiment can be represented as a universal curve that reveals a functional relation between these groups. To study the dependence of each of these parameters, we only need to vary the non-dimensional group now. For example, an experiment requires variation of diameter of pipe to half can be achieved by reducing the flow velocity to half, because in both cases the non-dimensional group will be changed to the same value. Therefore, using a pipe with a fixed diameter and using one fluid, we can study the influence of all parameters. This is the advantage of non-dimensional analysis in fluid mechanics. We will discuss more about non-dimensional group in a later video. In the next video, we will discuss about Buckingham's pi theorem, which is a systematic approach to identify the relevant non-dimensional group in a fluid mechanics problem, where there are n number of parameters involved. Thank you very much for listening and continue to listen to tied up video demonstrations.